Before we begin, please remember that this video is for informational and educational purposes only. The career paths and salary figures discussed are based on publicly available data and industry trends in the United States, but they are not a guarantee of employment or income. Your own success will depend on your individual skills, experience, location, and the job market. Always conduct your own thorough research. What if I told you that the single biggest piece of career advice for the last decade has been a lie? Not a malicious lie, but a deeply misleading one. A lie that has created a massive barrier, locking millions of talented Americans out of the most lucrative industry in modern history. The lie is this: to succeed in tech, you must learn to code. For years, we've been bombarded with this mantra. From Silicon Valley billionaires to coding boot camps promising a six-figure salary in 6 months. It's been hammered into our heads that the golden ticket to a high-paying job in computing is to become a software developer, a code monkey, a keyboard warrior staring at lines of Python or JavaScript all day. And while coding is an incredibly valuable skill, this obsessive focus on it has created a dangerous blind spot. It's like telling someone the only way to get rich in the auto industry is to become a mechanic who builds engines by hand. It completely ignores the designers, the strategists, the safety engineers, the supply chain managers, and the executives who actually run the entire operation. The truth is, some of the most powerful, influential, and highest-paying jobs in the entire American tech ecosystem require little to no coding at all. I'm talking about careers that start at $120,000 a year and can easily climb past $250,000, with far less competition than entry-level software developer roles. These are the hidden pathways, the back doors into the tech fortress that no one is talking about, because the learn-to-code industry is too loud. This video is your map to that hidden world. Over the next hour, I'm going to pull back the curtain on entire categories of computing careers you may have never even heard of. We're not talking about tech-adjacent roles like marketing or sales. We are talking about deeply technical, mission-critical computing jobs that form the backbone of companies like Google, Amazon, and Microsoft. For each one, I'm going to break down exactly what the job is, why it's so valuable, the kind of money you can realistically expect to make in the United States, and most importantly, the skills you need to get there, skills that often have more to do with logic, communication, and big-picture thinking than they do with writing flawless syntax. If you've ever felt like you missed the boat on tech, if you've ever looked at a coding tutorial and felt your eyes glaze over, if you have a logical mind but hate the idea of debugging code for 8 hours a day, then this is for you. This is your chance to pivot, to reskill, and to claim your piece of the tech gold rush without writing a single for loop. So let's start with the first hidden world. I call this category the architects. Imagine a massive, sprawling city. The software developers, the coders, they're the ones building the individual houses, the offices, the coffee shops. They're essential, of course. But who decides where the roads go? Who designs the power grid, the water systems, the communication networks that allow the entire city to function? Who makes sure that a skyscraper built on one side of town can seamlessly connect to the subway system on the other? That's not the construction worker. That's the city planner, the civil engineer, the architect. In the world of technology, this role is the cloud architect, the solutions architect, or the systems architect. These are the master planners of the digital world. They don't build the individual applications, but they design the vast, complex, and resilient systems that those applications live on. They are the ones who answer the big questions. When Netflix needs to build a system that can stream video to 200 million people simultaneously without crashing, a team of solutions architects designs the blueprint. When a major bank needs to move its entire financial infrastructure to the cloud securely and efficiently, a cloud architect draws the map. They work with the company to understand its goals, its problems, and its limitations. Then they use a palette of existing technologies, like services from Amazon Web Services, Microsoft Azure, or Google Cloud, as their building blocks. They are masters of putting these blocks together in the most efficient, secure, and cost-effective way possible. Their job is less about writing code and more about high-level problem-solving. It's a game of strategic chess, not a game of typing speed. They are the grand designers, the visionaries who see the entire forest, not just the individual trees. So what does it take to become one of these digital architects? You don't need a computer science degree focused on algorithms. Instead, you need something far more valuable: the ability to think in systems. Can you look at a complex problem and break it down into smaller, manageable parts? Can you communicate complex technical ideas to non-technical people like executives and project managers? Can you weigh the pros and cons of different approaches and make a decisive, well-reasoned choice? The pathway here isn't 4 years of college algebra and data structures. It's often through certifications. The most respected credentials in the industry, like the AWS Certified Solutions Architect, are the real degrees in this field. You can study for these on your own, proving your knowledge and your ability to design complex systems without ever writing a line of production code. You need a deep understanding of networking, storage, security, and databases, what they are and how they connect, but you don't need to be the expert who builds them from scratch. You're the general contractor, not the plumber or the electrician. You need to know what they do and how to hire them, but you don't do the wiring yourself. Now let's talk about the reason you're really here, the money. The compensation for these roles is staggering, precisely because they are so critical. According to data from Glassdoor and other industry sources, an entry-level associate solutions architect in the United States can expect a starting salary anywhere from $95,000 to $130,000. That's the starting line. Once you have a few years of experience and have proven you can design robust systems, you move into a mid-level architect role. Here, the average salary jumps to the $150,000 to $190,000 range. And for the senior and principal architects, the people designing systems for Fortune 500 companies, the true master planners, we are talking about a total compensation including bonuses and stock that regularly exceeds $250,000, $300,000, and in some cases even $500,000 a year. This is a career path where your value is tied directly to the scale of the problems you can solve. And in our increasingly digital world, the scale of those problems is growing exponentially every single day. The demand for people who can think big, who can design the digital infrastructure of our future, is exploding. Companies are desperate for these strategic thinkers, and they are willing to pay an enormous premium to get them. So, the first hidden world is that of the architect. A world where your ability to see the big picture, to solve complex puzzles, and to communicate your vision is far more valuable than your ability to write code. It's a world where you can become one of the most respected and highly paid people in tech by designing the stadium, not by laying the bricks. But what if you're not a grand designer? What if your mind isn't wired for sprawling blueprints and long-term infrastructure planning? What if your talents lie not in building but in defending? What if your instinct is to protect, to fortify, to stand as the guardian at the gate against the endless threats lurking in the digital shadows? Well, that brings us to our next hidden world, a career path where the stakes are even higher. The work is a constant battle of wits, and the paychecks are just as massive. The world of the digital protectors. And these protectors aren't just faceless geeks behind a screen. They are the digital equivalent of Navy SEALs, firefighters, and grandmaster chess players all rolled into one. Forget the stereotype of a programmer churning out lines of code in a quiet cubicle. The world of cybersecurity is a high-stakes, high-adrenaline career where you're not building something new. You're defending what already exists from an invisible, relentless enemy. Imagine a company, let's call it Ether Corp, a multi-billion-dollar healthcare technology firm. They hold the private medical records of millions of Americans. One Tuesday afternoon, an employee in accounting clicks a link in an email that looks like a routine invoice. It's not. It's the key. A silent, malicious piece of software, a digital ghost, slips past their defenses and begins to move through their network. It doesn't steal anything. Not yet. Just watches and waits. Now, who's the first line of defense? You might think it's some automated firewall, but the real high-value player here is someone who was in Ether Corp system last month. This is the penetration tester or the ethical hacker. This is the person companies pay an obscene amount of money. We're talking salaries starting at $120,000 and rocketing up past $200,000 for top talent, to think like a criminal. Their entire job is to legally and ethically hack into their own employer's systems. They use the same tools, the same mindset, the same devious creativity as the world's most dangerous cybercriminals. 3 weeks before that fateful click, an ethical hacker, let's call her Maya, found a vulnerability. She discovered that a specific type of software Ether Corp was using wasn't updated. She wrote a detailed report showing exactly how a hacker could exploit it, a step-by-step guide to breaking into the company's digital fortress. She explained the risk, she urged for a patch. But in the colossal machine of a megacorporation, the ticket was marked medium priority. It was put in a queue. Now it's Tuesday and the digital ghost is inside. The waiting is over. The malware activates and it begins encrypting every critical file it can touch. Patient records, financial data, research. It's all being locked away at lightning speed. This is a ransomware attack. A message flashes on screens across the company. Your files are encrypted. Pay $10 million in Bitcoin in 48 hours. or they will be deleted forever. Panic. Absolute sheer panic. The company is paralyzed. This is where the second protector enters the scene. This isn't the planner. This is the emergency room surgeon, the incident responder. This person is the corporate equivalent of a firefighter running into a burning building when everyone else is running out. Their phone rings at 3 a.m. on a Sunday during their kid's birthday party. It doesn't matter. When the alarm sounds, they go. The incident response team descends on EtherCorp's headquarters, setting up a war room. The air is thick with tension. They're working against a ticking clock, not just from the ransomware demand, but because every second the attacker is in their network, they could be doing more damage, stealing more data, creating more backdoors. The incident responder's job is triage. What's the damage? How did they get in? Are they still here? And most importantly, how do we kick them out and stop the bleeding? This isn't a coding job. This is digital forensics. It's about ripping apart network logs, analyzing malicious files, and understanding the attacker's tactics. It's high-pressure, high-stress detective work, and because of that, it's incredibly lucrative. Experienced incident responders are easily clearing $150, $170, even $200,000 a year, because when a company is losing $1 million an hour from downtime, paying someone $200,000 a year to fix it is a bargain. Let's say our team manages to isolate the infected systems and restore from backups. They stop the bleeding. They don't pay the ransom. But the crisis isn't over. The ghost might be gone, but how do you know if it left any friends behind? This is where our third protector comes in, perhaps the most fascinating of them all. The threat hunter. If the incident responder is the firefighter, the threat hunter is the deep-cover CIA operative. Their job is based on a terrifying premise. Assume you've already been breached. Assume the enemy is already inside your walls, hiding, waiting. A threat hunter doesn't wait for an alarm to go off. They proactively search for the faintest whispers of an attack. They look for anomalies, for behavior that is just slightly off. A user account logging in from 2 countries at once. A tiny trickle of data being sent to an unknown server in Eastern Europe. A process that's trying to disguise itself as a legitimate Windows service. This role is less about code and more about psychology and pattern recognition. You have to understand the why behind an attack. What are they after? What are their methods? You have to get inside the mind of your adversary. It's a cat-and-mouse game played across a global network. Because of this specialized, almost precognitive skill set, elite threat hunters are some of the highest-paid defenders in the industry, often commanding salaries well over the $200,000 mark. So the immediate danger at EtherCorp is over. But the company is shaken. They were vulnerable. They were blind. They can't let this happen again. This brings us to the master planners. First, the security architect. This is the person who designs the entire fortress. They look at the whole company, its people, its technology, its processes, and they design a comprehensive security strategy. What kind of walls do we need? Where do we put the gates? Who needs a key? How do we monitor the guards? The security architect decides what technologies to use, what policies to enforce, and how to build a system that is secure by design, not as an afterthought. This requires a deep understanding of networks, operating systems, and business operations. It's a role of immense responsibility, and it comes with a paycheck to match, frequently in the $180,000 to $250,000 range. And in today's world, that fortress isn't just in one building. It's in the cloud. So working hand in hand with the architect is our final protector, the cloud security engineer. This specialist focuses exclusively on securing data and applications that live on platforms like Amazon Web Services, Microsoft Azure, or Google Cloud. The cloud is a completely different battlefield with its own rules, its own vulnerabilities, and its own weapons. Companies are desperate for people who understand this new world. The demand is so ridiculously high that even mid-level cloud security engineers can command salaries of $160,000 or more. Look at the 5 roles we just covered: the ethical hacker, the incident responder, the threat hunter, the security architect, and the cloud security engineer. Notice a pattern? While some coding knowledge is helpful, their primary skill isn't writing software. It's about analysis, investigation, strategy, and a deep, almost obsessive curiosity about how things work and how they can be broken. It's a field where a background in criminal justice, military intelligence, or even psychology can be just as valuable as a computer science degree. These are the digital protectors, working in the shadows to keep our modern world from grinding to a halt. They are the hidden heroes of the information age, rewarded with some of the most stable, in-demand, and high-paying careers on the planet. But defending data is only one side of the coin. What about the data itself? What happens when you're not just trying to stop data from being stolen, but trying to make sense of an ocean of it so vast it's almost incomprehensible? What if you could use that data to predict the future, to shape human behavior, to create an entirely new form of intelligence? That's where our next hidden world lies. A world not of defense but of discovery. A world where the currency isn't just dollars but data. And in this world, the new prospectors aren't grizzled old men with pans and pickaxes. They're digital detectives and fortune tellers, armed with laptops and algorithms. They are the data analysts and data scientists, and they are sifting through mountains of digital noise to find pure gold. Let's get one thing straight. A data analyst and a data scientist are not the same thing, any more than a detective is the same as a prophet. They work with the same raw material data, but they ask fundamentally different questions. The data analyst is the detective. They look at the past. They arrive at the scene, a company's sales figures, website traffic, customer feedback, and they piece together what happened. They are masters of seeing the patterns that everyone else misses. They'll tell you why sales dipped in the third quarter, which marketing campaign brought in the most valuable customers, and what a spike in website clicks on a Tuesday afternoon really means. They are the storytellers of the past, using tools like SQL to query vast databases and visualization software like Tableau to turn endless spreadsheets into a story that a CEO can actually understand. They are invaluable. A great analyst can save a company millions by spotting a problem before it becomes a catastrophe. But the data scientists, they do something that feels a lot like magic. They look at the same data, the same past, and they build a machine to predict the future. Think about your Spotify Discover weekly playlist. How does it know you? How does it serve up that obscure band from the early 2000s that you instantly love but had never heard of? That isn't a person in a room somewhere making playlists. That's a team of data scientists who have built one of the most sophisticated recommendation engines on the planet. Here's how they did it. First, the data analysts did their detective work. They looked at billions of data points. What songs you play, what songs you skip in the first 10 seconds, what songs you add to your own playlists, what artists you follow. They found correlations. They discovered that people who listen to band A and band B also have a high probability of loving band C, even if those bands sound nothing alike. They found the clues. But that's just a clue. It's not a system. That's where the data scientist comes in. They take those clues and build a predictive model. They use a technique called collaborative filtering. It's a fancy term for a simple human idea. If person X has the same taste as you on 9 out of 10 songs, you'll probably like the 11th song they love but you've never heard. Now multiply that by 400 million users. The model isn't just comparing you to one person. It's comparing your listening DNA to millions of others, finding your musical soulmates you never knew you had, and then recommending what they're listening to. They also use natural language processing to analyze the text of what people are saying about music online, blogs, reviews, social media, to understand the feeling and context of a song. Is it a rainy day coffee shop song? Is it a late night highway driving song? The algorithm learns these nuances. The result isn't just a playlist. It's a multi-billion-dollar competitive advantage. It's the reason people stay subscribed to Spotify. It's a machine that predicts your desires before you even know them. And the people who build these machines, they are compensated accordingly. A skilled data analyst in the United States can expect to earn anywhere from $75,000 to over $120,000 a year, depending on experience and location. They are the bedrock of any data-driven company. But the data scientists, the ones building the crystal balls, senior data scientists at major tech firms regularly pull in salaries between $150,000 and $250,000, often with stock options that push their total compensation much, much higher. Why? Because if your model increases customer retention by just 1%, you've just created tens or even hundreds of millions of dollars in value for the company. You're not a cost center. You're a profit-generating oracle. And sitting right alongside them is another hidden role: the machine learning engineer. The data scientist might design the magical algorithm, but the machine learning engineer is the one who takes that beautiful, complex model out of the lab and actually builds it into a product that can handle millions of requests a second without crashing. They are the master builders, the ones who operationalize the magic, and their salaries are often on par with or even exceed those of data scientists. This isn't just about music or movies. This is happening in every single industry. In healthcare, data scientists are building models to predict disease outbreaks based on anonymized search query data. In finance, they build algorithms that detect fraudulent credit card transactions in milliseconds, saving consumers and banks billions. In logistics, they optimize shipping routes for companies like Amazon and FedEx, saving fuel, time, and money on a planetary scale. They are the invisible architects of efficiency and insight in our modern world. So how do you become one of these digital fortune tellers? You don't necessarily need a PhD in statistics anymore, though it helps. What you need is a deep-seated curiosity, the mind of a puzzle solver, and a willingness to learn the languages of data. Languages like Python and R are the go-to tools for data manipulation and modeling. SQL, the structured query language, is the key that unlocks the massive vaults of data where companies store their information. It's about learning to ask the right questions and then knowing how to torture the data until it confesses. The path isn't easy, but it's more accessible than ever. And it leads to a career where you're not just executing someone else's vision. You are the one providing the vision. You're the one looking at a chaotic sea of information and seeing the future. You are telling the business what to do next. This power of prediction is fundamentally changing our world. We've moved from simply storing information to analyzing it to now predicting what will happen next based on it. But there's another step in this evolution. A world beyond prediction. What happens when these complex models and massive datasets are used not just to understand our world, but to actively create it? What happens when the algorithm doesn't just recommend a product, but designs the product itself? What happens when the code begins to dream? That's the next frontier. A place where data and design collide to build the very fabric of our digital and physical reality. This frontier is already here. The code is dreaming right now, and the people teaching it how to dream, the ones conducting this digital orchestra, are called computational designers. And they are quietly becoming some of the most sought-after and highest-paid professionals in the entire tech landscape. Forget the image of a designer hunched over a drafting table or a Photoshop screen, meticulously drawing every line. A computational designer does something far more profound. They don't design the thing, they design the system that designs the thing. They are part architect, part programmer, part data scientist, and part artist. They write the rules, the logic, the very DNA of a design. Then they unleash the power of computing to explore thousands, even millions of possible outcomes, finding solutions so elegant and efficient that a human mind could never conceive of them on its own. Think of it this way. A traditional car designer might sketch a car body. A computational designer writes an algorithm. They tell the computer, I need a car body that can withstand a 40-mile-per-hour impact, has a drag coefficient of less than 0.25, uses the least amount of steel possible, and by the way, it needs to look beautiful. Then they hit run. The computer works through a process like digital evolution, generating generations of designs, testing them, breaking them, crossbreeding the best traits of each one, until it presents a final optimized form. A form that is not just designed but birthed from pure data and constraints. This isn't science fiction. Let me tell you a story about an airplane, specifically the Airbus A320. For years, a critical component of this plane was a simple metal partition that separates the passenger cabin from the galley. It was a solid, reliable but heavy piece of equipment. Airbus wanted to make it lighter. Every pound shed from an aircraft saves thousands of gallons of fuel and millions of dollars over its lifetime. So they handed the problem not to a team of engineers with pencils, but to a team of computational designers with algorithms. They fed the computer the exact physics of the part. They defined all the stress points, the load-bearing requirements, the connection points to the fuselage. They said, here are the absolute, unbreakable laws this part must obey. Now your mission is to create the lightest possible structure that satisfies all of them. Go. What the computer came back with was alien. It looked like something grown in a lab, not built in a factory. It was a bizarre web-like structure, full of strange curves and bone-like tendrils. It looked like a slice of a dragonfly's wing, or the inside of a bird's skeleton. It was a design that no human engineer in a million years would have ever thought to draw, because we think in straight lines, in solid blocks, in familiar shapes. The algorithm thinks only in pure, brutal efficiency. And the result? This biomorphic, alien-looking partition was 45% lighter than the original, yet just as strong. 45%. When scaled across their entire fleet, that single algorithmically generated part is projected to save Airbus and its airline customers hundreds of thousands of metric tons of carbon dioxide emissions. That is the power we are talking about. It's not just about making things look cool. It's about solving fundamental problems of engineering and physics by speaking the language of mathematics. This is why computational designers are in such high demand. In a world obsessed with optimization, they are the ultimate optimizers. They're being hired by Nike and New Balance to design running shoes with 3D printed midsoles that are perfectly tuned to a runner's gait. Lattices of material that provide cushion and support exactly where data says it's needed. They're being hired by the world's top architectural firms, like Zaha Hadid Architects, to design breathtaking skyscrapers that twist and curve in ways that would be impossible to draft by hand, all while optimizing for wind flow, sunlight exposure, and structural integrity. They're working in Hollywood, creating the complex digital worlds and creature effects that feel so real. They're in product design, creating everything from ergonomic chairs to lighter, stronger car chassis. They are the secret weapon behind the next wave of innovation, because they can solve problems at a scale and complexity that is beyond human capacity. So, what does it take to become one? This is where it gets interesting because there isn't one single path. This is a hybrid role for hybrid thinkers. Many come from traditional design fields like architecture or industrial design, and then layer on the computational skills. They learn visual programming languages like Grasshopper or Dynamo, which allow you to connect nodes and build logical flows without writing traditional code. Others come from a computer science background and develop an eye for aesthetics and physical design principles. The key skills are a blend of left brain and right brain. You need to understand systems thinking, how a change in one small rule can have a cascading effect on the entire design. You need to be fluent in data, able to interpret it, and use it to define your constraints. And you need to learn the core tools, 3D modeling software like Rhino or Revit, the visual programming plugins I just mentioned, and often a scripting language like Python to give you even more power and control. But here's the crucial part. You don't need to be a master of all of them from day one. You can start from your area of strength. If you're an artist, start with the visual tools. If you're a coder, start by applying your skills to a design problem. The value is in the intersection. And because that intersection is so rare, the compensation is significant. This isn't a typical junior designer role. Entry-level computational designer positions in the United States often start around $85,000 or $90,000, especially for those with a strong portfolio. Within a few years, as you move into a specialist or lead role at a major tech company, architectural firm, or manufacturing giant, you're looking at salaries well into the $130,000 to $180,000 range. And for the true experts, the principal designers who are leading entire divisions and inventing new design methodologies, compensation packages can easily exceed $250,000 a year. They are paid not for their time, but for their ability to generate immense value, to solve multi-million-dollar problems with a few elegant lines of logic. The future of this field is even more mind-bending. Right now, we're mostly giving the AI a problem to solve. The next step is for the AI to start finding the problems. Imagine an urban planning system that doesn't just design a more efficient intersection, but analyzes citywide traffic and demographic data to propose an entirely new, self-optimizing transportation grid. Imagine a software that designs personalized medicine, generating unique molecular structures to target diseases based on an individual's genetic code. This is the world the computational designer is building, a world that is not just smart, but responsive, adaptive, and generative. A world where the things we use are no longer static objects, but dynamic solutions, constantly evolving. But when you build a world run on these intricate self-designing systems, when your buildings, your cars, and your critical infrastructure are all products of a digital mind, you create a new kind of vulnerability. A single crack in this digital foundation, a single flaw in the logic, could bring everything crashing down in ways we've never seen before. So who are the guardians of this new world? Who are the digital sentinels standing watch over the code that dreams? They're not your typical IT security guys in a server room. They are a new breed of defender, operating on a completely different battlefield. This battlefield isn't in some far-off desert or a classified bunker deep underground. It's happening right now, in the invisible pathways that connect your phone to your bank, your hospital to its life support machines, and your power grid to your home. It's a silent, perpetual war fought in ones and zeros, and the casualties aren't just data. They're livelihoods, national security, and sometimes even lives. Imagine this. It's 3 a.m. at a major hospital in Chicago. A nurse tries to pull up a patient's chart for an emergency surgery. Denied. The screen flashes with the skull and crossbones and a message in broken English demanding a multi-million-dollar ransom in Bitcoin. The network is locked down. MRI machines, ventilators, heart monitors, all running on software that is now held hostage. The code that was meant to save lives is now being used as a weapon. This isn't a movie plot. This is a Tuesday for the digital defenders. This is where the first of our hidden careers emerges from the shadows. The penetration tester, or the more glamorous title, the ethical hacker. These are the good guys who are paid and paid very well to think and act like the bad guys. Their job is to break into their own companies before someone else does. They don't ask for the password. They find a way around it. They don't follow the rules. They exploit them. They are hired to be paranoid, to be relentless, to be the monster in the closet that finds every single weakness. A penetration tester might spend weeks trying to bypass a company's defenses. They might try to trick an employee into clicking a malicious link, a technique called social engineering. They might dive deep into the code of a web application, looking for a single misplaced semicolon that could unlock the entire kingdom. They are professional burglars with a get-out-of-jail-free card, testing the locks, checking the windows, and mapping out every possible way a criminal could get in. And the reason they command salaries often starting in the low six figures and soaring well beyond is because their value isn't just in the code they write, but in the mindset they possess. It's a unique blend of creativity, psychology, and technical prowess. You have to understand how systems are supposed to work so you can figure out a dozen ways to make them fail. You have to understand how people think so you can predict how they'll make mistakes. A single vulnerability discovered by an ethical hacker can save a company from a $100 million ransomware attack, a devastating data breach, or a stock-plummeting PR nightmare. They aren't just testing code. They're stress testing reality. But what if you want to stop the attacker before they even knock on the door? What if you could know what they were planning, who they were, and what tools they were going to use weeks or even months in advance? This isn't about building a better wall. It's about having spies on the other side of it. Welcome to the world of the cyber threat intelligence analyst. This role is less about hacking and more about espionage. These are the digital detectives and profilers of the 21st century. They live in the dark corners of the internet, monitoring hacker forums in Russia, tracking cryptocurrency wallets used by North Korean state-sponsored groups, and analyzing malware signatures coming out of China. Their job is to connect the dots that no one else sees. A threat analyst might see a sudden spike in chatter on a dark web forum about a new vulnerability in a specific type of software used by the financial industry. They'll see a new hacking tool being sold for Bitcoin. They'll notice that a known cybercriminal group has gone quiet. To most people, these are random, unrelated events. To a threat analyst, it's a pattern. It's the enemy massing its forces before an attack. They then take this raw intelligence and turn it into a story, a briefing for the executives and the technical teams. They'll say, a group we call Shadow Serpent is likely to target US banks within the next 60 days using a new technique that exploits this specific vulnerability. Here's how they operate, here's what they're after, and here's how we prepare. This isn't a coding job. It's an intelligence job. It requires an understanding of geopolitics, economics, and human psychology. You're not just fighting a piece of malicious code. You're fighting a hostile nation-state's cyber army or a sophisticated organized crime syndicate. The value here is immense. A company with great threat intelligence doesn't just react to attacks. It anticipates them, making them one of the most strategic and highly paid assets in the entire corporate structure. But even with the best defenses and the most brilliant intelligence, breaches still happen. The enemy gets through. The alarm bells ring. The hospital network is down. What happens then? You don't just shut it down and hope for the best. You call in the crime scene investigators. This is the domain of the digital forensics investigator. When a network is breached, it becomes a crime scene. And these investigators are the high-tech detectives who sweep in to figure out exactly what happened. Their job is to answer the critical questions. Who got in? How did they get in? What did they take? And are they still here? They work under immense pressure, sifting through terabytes of data, log files, memory dumps, network traffic, looking for the digital equivalent of a footprint or a fingerprint. They might recover a deleted file that shows the attacker's true IP address. They might analyze a piece of malware to trace it back to a known hacking group, like a ballistics expert matching a bullet to a gun. They have to be meticulous, methodical, and immune to panic. The evidence they uncover is critical. It helps the company patch the hole and kick the intruders out. It's used in multi-million-dollar insurance claims. And sometimes, it's handed over to the FBI to be used in federal indictments against international cybercriminals. This is where computing meets criminology. It's a field that requires an obsessive attention to detail and a passion for solving puzzles. You are, quite literally, finding the ghost in the machine. And because the integrity of a multi-billion-dollar company and the data of millions of customers rests on your findings, your expertise is valued at a massive premium. Penetration testers, threat intelligence analysts, digital forensics investigators. Three sides of the same valuable coin. They are the guardians, the spies, and the detectives of the digital age. Notice a pattern? While technical skill is the foundation, their true value, and their six-figure salaries, comes from something beyond coding. It comes from a mindset. The creative paranoia of the hacker, the strategic foresight of the spy, the meticulous logic of the detective. They operate in a world where the stakes are astronomical, protecting the invisible infrastructure that runs our entire country. They secure the code that dreams, but their work is a testament to the fact that the most powerful tool in computing isn't the computer itself. It's the human mind that operates it. But defending the city is one thing. What if you're the one who designs the blueprints? What if you're not just protecting the systems, but architecting them from the ground up, building the digital skyscrapers and highways of tomorrow? Because beyond the coders and their defenders lies another, even more lucrative world. A world not of defense but of creation on a massive global scale. This is the world of the architect. Not the kind who designs buildings with steel and glass, but the one who designs entire technology ecosystems with servers, databases, and APIs. We're talking about the cloud solutions architect, and their job is to look at a blank digital canvas, a business problem, and design the masterpiece solution that will run on it. If a software developer is a master carpenter, meticulously crafting a beautiful, functional piece of furniture, the solutions architect is the master builder who designed the entire house. They decided where the load-bearing walls go, how the plumbing connects, where the electrical grid runs, and how the whole structure can withstand a hurricane. The carpenter's skill is essential, but the architect's vision determines if the house stands or falls. Imagine a brilliant chef. They can cook a single perfect steak. That's the coder. They execute a specific task flawlessly. But the solutions architect? They are the executive chef who designs the entire menu. They don't just think about the steak. They think about the appetizer that complements it, the wine that elevates it, the supply chain for the ingredients, the efficiency of the kitchen staff, the cost of every plate, and the overall dining experience for 1,000 customers a night. They operate on a completely different level of abstraction. They are less concerned with the specific code used to, say, process a credit card, and more concerned with a dozen critical questions. Should we use AWS, Google Cloud, or Microsoft Azure for this? What happens if our payment processor goes down? How do we scale from 10,000 users to 10 million users overnight without anything breaking? How do we ensure we're compliant with data privacy laws in California and in Germany simultaneously? These are not coding problems, they are architectural problems. Answering them wrong can bankrupt a company. Answering them right can turn a startup into a unicorn. Let's make this real. Picture a new streaming service. Let's call it Stream Now. They have a fantastic app, built by a team of razor-sharp coders. It works great for their first 50,000 users. But then they get a surprise celebrity endorsement. Their user base explodes. Suddenly, 3 million people are trying to log on at once. The app crashes. The website goes down. The database melts. The coders are in a panic, trying to patch holes in a sinking ship. The company is losing millions in subscription revenue and, more importantly, user trust. This is a classic success disaster. This is where the solutions architect steps in. They aren't brought in to write code. They're brought in to think. They get in a room with the CEO, the head of marketing, and the lead engineers. The architect listens. They learn the business goals. 5 million users by next quarter, expansion into Europe, launching a live sports feature. Then they go to the whiteboard. They don't draw lines of code, they draw boxes and arrows. This box is a user authentication service. This one is a video transcoding pipeline. This one is a recommendation engine powered by machine learning. They decide that for the user database, they need something like Amazon's DynamoDB for its incredible scalability. For the video content, they'll use a content delivery network with nodes all over the world, so a user in Tokyo gets the same fast load time as a user in Ohio. They design a system that is loosely coupled, meaning if the recommendation engine fails, it doesn't bring down the entire ability for someone to log in and watch a movie. They build a blueprint for a resilient, scalable, and cost-effective global streaming platform. Notice, their core value wasn't in their ability to write Python or Java faster than anyone else. Their value was in their breadth of knowledge. They knew the pros and cons of 20 different database technologies. They understood the intricacies of global internet traffic. They could calculate the projected monthly cloud bill for 5 different designs and explain to the CFO why the more expensive option would actually save the company money in the long run. They are the ultimate translator, speaking the language of business value to the executives and the language of technical implementation to the engineers. They are the bridge between the boardroom and the server room. To become a solutions architect, you don't need to be the best coder on the team, but you need to have been in the trenches. You need to understand how software is built, what can go wrong, and how different technologies fit together. It's a role that heavily favors experience and wisdom over raw coding speed. You climb this ladder not by becoming a better coder, but by becoming a better thinker, a better planner, and a better communicator. Your primary tools are not a keyboard and a compiler. They are a whiteboard, a diagramming tool, and your ability to persuade a room full of smart people that your vision is the right path forward. And because of this immense responsibility, the strategic leverage, the compensation is staggering. A seasoned solutions architect in the United States routinely earns between $180,000 and $250,000 a year. Top-tier architects at major tech companies, the ones designing systems used by billions, can push well into the $300,000 range and beyond with stock options. Why? Because a single good decision from an architect can save a company $10 million in cloud costs or unlock $100 million in new revenue. A single bad decision can lead to a catastrophic outage that erases the company's stock value. They are paid for their judgment, and in the high-stakes world of cloud computing, good judgment is one of the most valuable commodities on the planet. This is a career of immense influence. You are setting the technical direction for entire divisions, sometimes for an entire company. You're not just building a feature. You're building the factory that allows hundreds of other developers to build features for years to come. You are creating the digital foundation. But a perfectly designed skyscraper, a flawless digital factory, is just an empty shell without its most valuable asset: the information, the data, the lifeblood flowing through its digital veins. What happens when that lifeblood becomes a tidal wave? An unimaginable flood of data, so immense it threatens to drown the very systems you so carefully designed to hold it. Who tames that flood? And more importantly, who learns how to turn that chaotic, roaring torrent into pure, refined gold? Enter the data engineer. Think of them not as a coder in the traditional sense, but as a grand architect and a master plumber for the digital age. When a company like Amazon processes millions of transactions a minute, or when YouTube ingests 500 hours of video every 60 seconds, that data doesn't just magically appear in a neat, orderly spreadsheet. It's a chaotic, messy, high-velocity torrent. The data engineer is the one who designs and builds the massive, industrial-scale pipelines, reservoirs, and purification plants to handle that flood. They use powerful tools like Apache Spark and Kafka to build systems that can drink from a fire hose without overflowing. They are masters of the cloud, orchestrating vast resources on Amazon Web Services, Google Cloud, or Microsoft Azure to store and process petabytes of information. They don't just build the dam. They build the entire waterworks for a digital metropolis. Their mantra is ETL. Extract, transform, load. They extract raw, often garbled data from countless sources, transform it into a clean, structured, and usable format, and load it into a central repository like a data warehouse. Without the data engineer, there is no data. The entire multi-billion-dollar industry of data analytics and artificial intelligence grinds to a halt. They are the foundational layer, the unsung heroes who make everything else possible. And because they are so fundamental, so critical, they are paid exceptionally well. A skilled data engineer in the US can command a salary that easily rivals and often surpasses that of a top-tier software developer, with senior roles comfortably pushing deep into the $200,000 range and beyond. They are in a constant, desperate state of demand because every company in every sector is waking up to the fact that their data is useless if it's trapped in a swamp. The data engineer is the one who drains the swamp. Once the engineer has built the pristine, crystal-clear reservoir of data, the data analyst steps up to the shore. If the engineer is the architect, the analyst is the detective, the investigative journalist. They are given a specific question. Why are our sales down 15% in the Northeast this quarter? Or which marketing campaign is giving us the best return on investment? They don't need to build the system, but they need to know how to navigate it with surgical precision. Their primary weapon is SQL, the structured query language, which they use to speak directly to the database, asking it questions and commanding it to reveal its secrets. They pull the relevant information, And then, using tools like Tableau or Microsoft Power BI, they become storytellers. They transform raw rows of numbers into compelling visual narratives, interactive dashboards, insightful charts, and clear, concise reports. They are the translators who bridge the gap between the technical world of data and the strategic world of business decision-making. They might discover that the sales dip in the Northeast correlates perfectly with a competitor's new product launch, or that a single Instagram ad campaign is outperforming all of their television spots combined. They provide the what and the why that guides the entire company. You don't necessarily need a deep computer science background to excel here. A logical mind, a curious nature, and a passion for finding the story hidden in the numbers can make you an indispensable asset. And while it's often a gateway into the data world, a senior data analyst with deep business domain knowledge is a strategic powerhouse, earning a salary well into the six figures by providing the clarity that leaders need to navigate treacherous market waters. But what if you want to go beyond what happened in the past and start predicting the future? What if you want to not just analyze the game, but create a model that can predict the winner before the game even starts? For that, you need the third and perhaps most mythologized member of our trio, the data scientist. The data scientist takes the clean, organized data from the engineer and the contextual understanding from the analyst, and they add a powerful new ingredient: advanced mathematics and the art of machine learning. They are the futurists, the oracles of the modern age. They build the complex algorithms that power the world around you. When Netflix recommends a movie you inexplicably love, that's a data scientist's recommendation engine at work. When your bank flags a fraudulent transaction on your credit card moments after it happens, that's a data scientist's predictive model standing guard. They answer the most challenging, forward-looking questions. Based on current viewership trends, what kind of TV show should we invest $100 million in producing next? Or, which of these 10,000 potential drug compounds is most likely to be effective against a new disease? They use languages like Python and R, along with sophisticated libraries like TensorFlow and PyTorch, to build and train artificial intelligence models. They are part statistician, part computer scientist, and part business strategist. Because they operate on the cutting edge, turning raw data not just into insight, but into predictive power and automated intelligence, their value is immense. This is the role famously dubbed the sexiest job of the 21st century, and the salaries reflect that hype. It's the land of $200,000 starting salaries for PhD grads, where specialists in fields like natural language processing or computer vision can command compensation packages that rival those of top executives. So you have the engineer, the master builder who constructs the entire data infrastructure. You have the analyst, the sharp-witted detective who investigates the past and present to find actionable insights. And you have the scientist, the visionary inventor who builds crystal balls to predict the future. Three distinct roles, three different mindsets, all revolving around the same raw material: data. They are a team, a trinity of talent that is transforming every industry on the planet. And the best part? While they are deeply technical, their focus is less on building a user-facing application from scratch and more on harnessing the invisible forces that power our world. They prove unequivocally that you can build an incredibly lucrative and impactful career in computing that goes far beyond traditional coding. But this raises a critical question. All this data, all these applications, all these complex systems, where do they live? They don't just float in the ether. They run on a physical and virtual infrastructure of staggering complexity, an invisible backbone that keeps the entire global economy humming, 24 hours a day, 7 days a week. What happens when a single component in that backbone fails, threatening to bring a billion-dollar enterprise to its knees? Who are the elite specialists that can not only build this hyper-resilient infrastructure, but also automate it, scale it, and make it heal itself? Who are the modern-day titans holding the entire digital world on their shoulders? They are the DevOps engineers, the site reliability engineers, and the cloud architects. These aren't just job titles, they are philosophies. They represent a revolutionary shift in how technology is built and maintained, a shift born from the chaotic, fragmented world of old-school tech. See, for decades, the digital world was split by a massive wall. On one side, you had the developers, the creators, the artists crafting brilliant new features in their isolated workshops. On the other side, you had the operations team, the guardians, the mechanics tasked with keeping the live systems running, often treating any new code from the developers as a potential threat, a bomb waiting to explode. This divide was a recipe for disaster. Developers would throw their code over the wall, and when it inevitably broke in the real world, the finger-pointing would begin. Operations would blame the buggy code. Developers would blame the broken environment. Releases were slow, painful, and terrifying. Innovation crawled at a snail's pace. Businesses lost millions. The entire system was fundamentally broken. And in the crucible of this conflict, a new kind of professional was forged. Enter the DevOps engineer. They are not just coders and they are not just system administrators. They are the combat engineers who demolish that wall and build a superhighway in its place. Their mission is to fuse development and operations into a single, seamless, automated flow. They are the masters of the CI/CD pipeline, continuous integration and continuous deployment. Think of it like a hyper-advanced assembly line for software. A developer writes a piece of code, and the moment they save it, this automated pipeline snatches it up. It runs thousands of tests, checks for security vulnerabilities, packages it, and if everything is perfect, deploys it to millions of users, all without a single human clicking a button. This isn't a process that takes 6 months anymore. It can happen in 6 minutes. They achieve this magic through a concept called infrastructure as code. Instead of manually setting up servers, clicking through confusing web consoles, and praying they configured everything correctly, a DevOps engineer writes code that describes the entire system. They write a blueprint, a recipe that can summon a complete, perfectly configured data center out of thin air on Amazon Web Services or Google Cloud. Need to handle a sudden spike in traffic? They don't panic. They change one line of code, and 100 new servers spring to life. Need to create an exact replica of the entire company's infrastructure for testing? They run a script. This power is monumental. It turns infrastructure from a fragile, hand-built artifact into a reproducible, disposable commodity. They are the force multipliers who can make a team of 50 developers 10 times more productive and 1,000 times more reliable. And for that, they are compensated handsomely. A skilled DevOps engineer in the US can easily clear $150,000, with senior roles comfortably pushing past $200,000, because they don't just fix problems, they build the machine that prevents problems from ever happening. But what if you take this philosophy to its absolute extreme? What if you recruit the most brilliant software engineers and give them a single terrifying mandate? Make our global systems unbreakable. That's when you get a site reliability engineer, or SRE. The role was invented at Google when they faced a problem no one had ever had before. How do you keep a service used by billions of people running flawlessly 24/7? Their answer was revolutionary. Treat operations as a software engineering problem. An SRE's world is governed by data, not gut feelings. They live and breathe service-level objectives and error budgets. An error budget is one of the most powerful ideas in modern tech. Instead of chasing the impossible dream of 100% uptime, an SRE team agrees with the business on an acceptable level of reliability, say 99.99% uptime. That remaining 0.01% is their error budget. It's a literal budget of downtime they are allowed to spend. As long as the system is stable and they haven't spent their budget, developers are free to launch new features at will. But the moment a bad update causes an outage and they spend that budget, an automatic freeze is triggered. All new feature launches are halted until the SREs have fixed the underlying instability and earned back their reliability. It's a brilliant, self-regulating system that perfectly balances innovation with stability. There's no more arguing. The data decides. SREs are obsessed with eliminating toil, the repetitive, manual, tactical work that plagues traditional operations teams. They have a rule. If you have to do the same manual task 3 times, you automate it the 4th time. They are fundamentally driven to engineer themselves out of a job, building sophisticated software that can detect, diagnose, and even heal system failures automatically. When something does go catastrophically wrong, they lead a blameless post-mortem. The goal is not to find a person to fire. It's to find the systemic reasons that allowed the failure to happen and re-engineer the system, so that entire class of problem can never happen again. This unique blend of elite software engineering and systems expertise makes SREs some of the most sought-after and highly paid professionals in the industry. Salaries often start in the high 100s and can soar well past $250,000 for principal engineers, because they are the ultimate guarantors of a company's digital existence. But who designs the city before the DevOps engineers build the highways and the SREs install the power grid? Who looks at the empty landscape of the cloud and decides where the skyscrapers, residential zones, and industrial parks should go? That is the domain of the cloud architect. They are the master planners, the grand strategists of the digital world. While an SRE might worry about the latency of a single service, A cloud architect worries about the design of the entire global network. They answer the monumental questions that can make or break a company. How do we build a system that can serve 10,000 users today, but 100 million next year, without a complete redesign? How do we choose between dozens of different database technologies, knowing the wrong choice could cost us millions in a few years? How do we build a financial trading platform on the cloud that is not only lightning fast, but also meets a labyrinth of federal security and compliance regulations? The cloud architect is the one who has the experience, the vision, and the deep technical knowledge of platforms like AWS, Azure, and GCP to draw the blueprint. They have to think about cost optimization, security, data flow, resilience, and a dozen other factors simultaneously. They are often the most senior technical voice in the room, translating complex business requirements into a concrete technical design that teams of engineers will then spend years building. This isn't a role you land straight out of college. It's a destination, the culmination of years of hands-on experience, and their compensation reflects that. Cloud architect salaries routinely start near the $200,000 mark and climb significantly higher, as their decisions carry the weight of millions, sometimes billions, of dollars of business impact. These three roles, DevOps, SRE, and Cloud Architect, form the powerful hidden backbone of the modern digital enterprise. They aren't building the app you use, they're building the universe in which that app lives. They've shifted their mindset from just writing code to building automated, resilient, self-healing systems. But how does one even begin to acquire this almost mystical set of skills? What does the path look like from being a junior coder, or even a total beginner, to becoming one of these architects of the invisible world? The path isn't paved with arcane secrets or guarded by gatekeepers in ivory towers. It's a path of deliberate learning, a shift in perspective from writing a single piece of code to understanding the entire universe in which that code lives and breathes. It begins not with the most advanced tools, but with the most fundamental principles, the bedrock that so many aspiring developers, in their rush to build the next hot app, completely overlook. First, you must learn to think in systems. This is the absolute, non-negotiable foundation. A coder thinks about a function. A software engineer thinks about an application. An architect and SRE, a true systems thinker, thinks about the entire chain of events. They see the user clicking a button not as a single action, but as the start of a massive, intricate dance. A DNS lookup, a TCP handshake, a request hitting a load balancer, being routed to one of 100 web servers, which then queries a database replica, which in turn checks a cache, all while logs are being streamed to a central collector and metrics are being scraped by a monitoring service. To them, it's not a series of independent components. It's one living, breathing organism. And you can't protect an organism or make it stronger if you only understand one of its cells. To build this systems thinking muscle, you have to get your hands dirty with the two pillars that hold up the entire digital world: networking and operating systems. Not just a surface-level understanding, I mean a deep practical knowledge. You need to understand how data actually travels across the internet. What is the TCP/IP suite really? What happens during a DNS query? Why is HTTP/3 using QUIC instead of TCP? How does a load balancer actually make its decisions? This isn't just trivia. It's the language of reliability. When a system is slow, knowing these fundamentals is the difference between blindly restarting a server and diagnosing a saturated network link in a specific data center. And then there's the operating system, which for nearly every serious system in the world means Linux. You must become fluent in the command line. It's not a retroaffectation. It's the most powerful and direct way to interact with a machine. You need to understand how Linux manages processes, memory, and storage. What are nodes? What's the difference between a soft link and a hard link? How do you trace system calls to see what a program is really doing? This depth of knowledge is your superpower. It's what allows you to debug the undebuggable, to optimize the unoptimizable, and to build systems that are truly resilient because you understand the very ground they stand on. This leads to a powerful mental model for career growth known as the T-shaped professional. Imagine the letter T. The vertical bar is your deep, specialized expertise. Maybe you are a phenomenal Python developer, a database guru, or a security expert. That's your core strength. But the horizontal bar represents your broad knowledge across many other domains: networking, cloud infrastructure, monitoring, CI/CD. The junior developer is just an I. They're deep in one thing but lack the context of everything else. The high-impact, high-value roles we're talking about belong to the T-shaped individuals. They have their deep specialty, but they can also have an intelligent conversation with the networking team, understand the constraints of the storage admins, and appreciate the goals of the product managers. This breadth of knowledge is what allows them to design and build solutions that don't just work in a vacuum, but thrive in the complexity of the real world. So, how do you build your T? It's a structured, deliberate process. Step 1 is to solidify your foundation. If you're a coder, go beyond your framework. Build something, anything, but then take on the challenge of deploying it yourself from scratch. Don't use a fancy all-in-one platform. Rent a cheap virtual private server online for $5 a month. SSH into it. Install and configure a web server like Jinx. Set up your database. Secure it with a firewall. Buy a domain name and figure out how to point it to your server. This single hands-on project will teach you more about systems, networking, and operating systems than a dozen online courses. You will fail. It will be frustrating. And it will be the most valuable learning experience you've ever had. Step 2. Pick a cloud and go deep. The modern world runs on AWS, Azure, and Google Cloud. You can't be an expert in all three, so pick one to start. In the US market, AWS still holds the dominant share, making it a safe bet. Now, people love to debate certifications, but here's the truth. A certification without hands-on experience is useless. However, studying for a certification is one of the best structured learning paths you can find. It forces you to learn the services, the vocabulary, and the right way to build things according to the platform's best practices. Start with a foundational cert like the AWS Solutions Architect Associate. Don't just cram to pass the test. Use it as a curriculum. For every service you study, open the console and actually build something with it. This combination of structured learning and hands-on practice is pure gold. Step 3 is to master the tools of automation and scale. This is where you start building the horizontal bar of your T. First, infrastructure as code, specifically Terraform. This is the idea that you should manage your servers, networks, and databases with code, just like you manage your application. It allows you to create, update, and destroy entire environments in a repeatable, predictable way. It's one of the most transformative technologies of the last decade. Next, containers and orchestration, which means Docker and Kubernetes. Think of Docker as a standardized shipping container for your code. It bundles your application and all its dependencies together, so it runs the exact same way on your laptop, a test server, or in production. Kubernetes is the global logistics system that manages tens of thousands of these containers across a fleet of machines. It handles scaling, self-healing, and deployments. Learning these two is no longer optional. It is the standard for modern software delivery. Finally, learn a CI/CD, or continuous integration and continuous deployment tool. This is the automated assembly line that takes a developer's code, runs tests, packages it into a Docker container, and deploys it using Kubernetes. Tools like GitHub Actions or GitLab CI are a great place to start. The fourth and most critical step is a mindset shift. The tools change, but the mindset is timeless. You must cultivate an intense sense of ownership. When something breaks, your job isn't just to fix it. It's to understand the root cause so deeply that it can never happen again for the same reason. This is the core of a blameless postmortem culture. You have to become a fantastic documenter. The knowledge in your head is useless if you get hit by a bus. Writing clear diagrams, runbooks, and architectural decision records is how you scale yourself and your team. And you must start thinking in terms of metrics, not just features. Learn about service level objectives, or SLOs. Instead of vaguely saying the site should be fast, you define that 99% of homepage loads must complete in under 200 milliseconds. This is the language of business. It's how you translate technical performance into user happiness and business impact. It's the very heart of site reliability engineering. This roadmap, from fundamentals to cloud to tools to mindset, is the journey. It's not easy, and it doesn't happen overnight. It is a constant process of learning and building, of breaking things and then truly understanding why they broke. This is the path from being a coder to an architect. But what does this journey actually feel like? And more importantly, as AI begins to write its own code and manage its own systems, are these architects of the invisible world building their own replacements? We'll tackle that and the future of computing careers in our final part. The fear is palpable, isn't it? The idea that the very tools we create to build the future might one day render us, the builders, obsolete. It's the ultimate paradox. The master craftsmen forging the key to their own obsolescence. But to see artificial intelligence as merely a replacement for human ingenuity is to fundamentally misunderstand the nature of the game we're now playing. AI isn't the endpoint. It's the next evolution of the toolkit. Think of it this way. For centuries, architects designed buildings with pen and paper. They drew every line, calculated every load, and painstakingly rendered every facade. Then came computer-aided design, or CAD. Suddenly, a machine could handle the tedious drafting, the complex calculations, the 3D modeling. Did this eliminate the architect? No, it liberated them. It freed them from the tyranny of the mundane and allowed them to focus on what truly matters. The vision, the creativity, the understanding of human space, the interplay of light and material. The value shifted from the act of drawing to the art of designing. This is precisely the shift happening in computing right now. AI is becoming our CAD. It can write boilerplate code, optimize databases, and even identify security vulnerabilities faster than any human. But it cannot, and will not for a very long time, replace the architect. It cannot understand a company's 5-year business strategy and translate that into a resilient, scalable, and cost-effective cloud infrastructure. It cannot sit down with a frantic CEO and a skeptical board of directors, listen to their fears and ambitions, and then design a cybersecurity posture that protects their assets while enabling growth. These roles we've explored: the cloud solutions architect, the DevOps engineer, the cybersecurity analyst, the site reliability engineer, are increasingly less about the syntax of a programming language and more about the syntax of a business. They are about translation, strategy, and foresight. An AI can be given a well-defined problem and produce a solution. But the highest-paying, most resilient careers of the future belong to the people who can define the problem in the first place. That is a fundamentally human skill. It requires empathy, domain knowledge, and the ability to see the big picture, connecting dots that don't yet appear to be on the same page. As AI handles more of the low-level implementation, the demand for high-level human judgment will skyrocket. We are entering the era of the system thinker. The value isn't in knowing how to configure a single server. It's in understanding how 1,000 servers, a dozen microservices, 3 different cloud providers, and a complex web of APIs all interact to deliver a seamless experience to a user on their phone in milliseconds. That is not a coding problem. That is a symphonic problem. It requires a conductor, not just a sea of individual musicians. The AI can play the violin perfectly, but it can't write the symphony or lead the orchestra. Furthermore, the very existence of powerful AI creates an entirely new class of high-stakes challenges that demand human oversight. Who is responsible when a self-driving car's AI makes a fatal ethical choice? Who ensures that an AI used for loan applications isn't perpetuating historical biases? Who designs the off switch for an AI that becomes too powerful or unpredictable? These are not technical questions. They are deeply human, ethical, and philosophical questions with billion-dollar consequences. This gives rise to new roles we're only just beginning to define: AI ethicist, machine learning governance specialist, AI safety researcher. These are professionals who blend deep technical understanding with philosophy, law, and social science to steer the ship of progress responsibly. And this is just the beginning. The horizon of computing is expanding, not contracting. We're on the cusp of the next great platforms. Quantum computing, for example, is not just a faster version of what we have now. It's a fundamentally different way of processing reality. The quantum systems architect will need to be part physicist, part computer scientist, and part visionary, designing algorithms for problems that are currently unsolvable. Consider the concept of the digital twin, a perfect real-time virtual replica of a physical object like a jet engine, a power grid, or even an entire city. The digital twin architect will design and manage these virtual worlds, allowing us to simulate, predict, and optimize the physical world with unprecedented accuracy. This isn't science fiction. It's the next frontier of industrial and urban design. And at the very top of the enterprise, we'll see the rise of the Chief AI Officer, a C-suite executive whose sole job is to strategically integrate artificial intelligence across every facet of a business, from marketing and finance to logistics and product development. This person isn't a coder. They are a business strategist with a PhD-level understanding of what AI can and cannot do. So, are the architects of this new world building their own replacements? The answer is a resounding no. They are building their own leverage. They are creating tools that amplify their own intelligence, automate the repetitive, and free them up to work on problems of a higher order. The fear of being replaced by AI is a fear born from a 20th century mindset, where value is tied to the execution of a specific, repeatable task. In the 21st century, durable value lies in the skills that machines find hardest to replicate: creativity, critical thinking, strategic planning, and complex communication. The journey we've taken through this hidden world of computing careers reveals a powerful truth. The most future-proof skill you can develop is not mastery of a single programming language or a specific software tool. Those will inevitably change. The ultimate meta skill is the ability to learn, adapt, and solve ambiguous, multifaceted problems. It's about becoming a professional problem solver who uses technology as their primary medium. The question is no longer, should I learn to code? The question now is, what kind of complex problems do I want to solve? Do you want to build the invisible infrastructure that powers global commerce? Do you want to defend nations and corporations from digital threats that could cripple society? Do you want to orchestrate the complex dance of software development and deployment that brings new ideas to life at lightning speed? This is the real opportunity to move beyond the code, to look at the entire system, the entire business, the entire human experience and ask, how can I make this better? The people who can answer that question, who can design the blueprint for that better future, will not just have a high-paying job. They will have a career that is resilient, rewarding, and right at the center of shaping the world to come. The future of computing isn't about being a cog in the machine. It's about being the architect of the machine itself. And that is a job that will never be automated.